Welcome, everyone. On behalf of my co-host, Dr. Jesse Allen Hellman, and myself, Surya Das, I'd like to extend a very warm welcome to everyone who is here attending the 2021 Canadian Association of Physicists Lecture Tour, first lecture. My name is Surya Das. I am a professor of physics at the University of Lethbridge, Alberta, Canada. And it's my great pleasure to welcome again everyone to the first lecture of today. So first things first, please submit your questions during and after your talk through the web form on YouTube. You should be able to see the French subtitles of the presentation as we go along. So before it's my great pleasure to introduce the speaker of today. But before that, let me talk a couple of minutes on the Canadian Association of Physicists, the CAP, who is organizing this lecture and the series of lectures as they do every year. The CAP is a national network of 1,700 member physicists working in Canadian institutions and industry. It is the voice of Canadian physicists to the government, granting agencies, and international societies. It's a sponsor of and supporter of a host of Canadian physics events, which includes the CAP Annual Congress, National Student Physics Conferences, and the publication Physics in Canada. CAP works great for the students as well. For example, it offers a professional certification. It organizes student conferences, CUPC and CCUWIP, the graduate student conferences. It organizes the university prize exams, scholarships, and has awards for the best student paper competitions at the CAP Congress, etc. I would encourage all students, undergraduate and graduate Canadian physics students, to consider joining CAP. It's great. It's free during the bachelor's and for 1 year free for graduate students. So I would encourage everyone to join CAP if you can. Right. With that, again, it's my great pleasure to introduce today's speaker to the first CAP lecture of 2021. Today's speaker, Dr. Stephanie Simmons, is an assistant professor, the Canada Research Chair, as well as a CFAR Fellow, and based out of the Department of Physics at Simon Fraser University. Dr. Simmons is the founder and chief of quantum officer of Photonic Incorporated. At Simon Fraser, Dr. Simmons is the group leader of the Silicon Quantum Technology Research Group. Dr. Simmons earned her PhD in material science at Oxford University in 2011 and was also the Clarendon Scholar, where she was the Clarendon Scholar, and earned a Bachelor of Math from the University of Waterloo. She was a postdoctoral research fellow of the Electrical Engineering Department at the University of New South Wales in Australia and completed her junior research fellowship and Gladstone Research Fellowship from St. John's College in Oxford. Dr. Simmons joined the Simon Fraser University as the Canada Research Chair in quantum nanoelectronics in 2015. Dr. Simmons works on silicon-based spin quantum bits, which are also known as qubits, with the particular aim to develop telecom-compatible quantum technologies, scalable quantum technologies. Her work on silicon quantum technologies was awarded a Physics World Top 10 Breakthrough of the Year prize in 2013 and again in 2015. She was named one of Canada's top 40 under 40 for 2020. Her work has been covered widely in the media, which includes publications such as the New York Times, the CBC, the BBC, Scientific American, New Scientists, and several others. So without further ado, I would thank Dr. Simmons for giving this talk, and I would like to welcome Dr. Simmons to start the presentation. I'll stop sharing my screen, muting myself, but we are around attending. So thanks, everyone. Dr. Simmons.
Hi. Well, hello, everybody. Thank you very much for coming here. and I am very excited to be able to give this talk. So I'm going to be talking to you about the international race for a quantum computer. And I have been working on this for quite some time now, and it's very much an exponential growth industry. There's lots of interest now growing from all sectors, and you've probably heard things about this in the news. It seems like there's a breakthrough for quantum computing every other week. And it does seem to get quite a bit of media attention. But what people don't really realize is they don't have a good visual of what it actually is. Like, what is a real quantum computer? So if you were to Google what is a quantum computer, you'll see a few different images. You'll see a bunch of apparently blue versions of classical computers. That's what people think of when they think of as quantum. It's just glowing, but classical. You may see some gray or blue abstract patterns where it's just trying to visually represent something that people can't really get their heads around, so may as well go abstract. And most recently, you'll see quite a bit of imagery around some of the hardware which supports some quantum technologies, but usually it's the surrounding environment that they picture rather than the actual any quantum chips. So they'll show you dilution refrigerators with a lot of wires, mainly as an act to be intimidating, I feel. But really, what is quantum computing? Well, it's physical. It is a physical thing. Information is physical. It is represented by physical things. And when you perform operations on any of the data that we have today, whether it be your phone or your computer, these are actual physical operations happening to physical bits. Like bits are zeros or ones in a digital form represented in physical reality. So really what we have here is the opportunity to think about the full spectrum of what's possible according to the laws of physics, rather than just restricting ourselves to the classical physics and classical manipulation of data. We can open it up to broader categories. And maybe one of the most well-known quantum properties is as epitomized through Schrodinger's cat, where you have this seemingly incompatible configuration that can happen at the same time, this principle of superposition, right? So according to Schrodinger's cat, it was meant to be an exercise to show how ridiculous quantum mechanics is when scaled to large systems. But it is true at the microscopic scale for many of the systems we work with, the idea that you can be in two incompatible configurations at the same time. So for a cat, it could be simultaneously both dead and alive. You would think that these things are simultaneously incompatible. But when we talk about quantum particles, this is absolutely routine. You can have things that are in superposition of two different spatial configurations. Say an electron could be here or here. And this is very routine for many of the experiments that we have. Even at the undergraduate level, you can show and demonstrate the existence of superposition for individual quantum particles. And so for an information perspective, the idea is, can we harness this? Can we harness the ability for quantum states to be in multiple configurations at once, subject to all of the laws of quantum mechanics, of course, to get some sort of computational advantage? Now, the answer is yes, we can. And we've been working to build these systems for a long time. And that comes with a bit of a caveat. When you look at Schrodinger's cat, when you observe the system, it can only ever report being in one of the multiple configurations, right? So when you open the box, Schrodinger's cat has to tell you that it's dead or alive. So these are the results that you get at the end. It depends upon, you have to measure it. So the trick is to design quantum algorithms that make use of this temporary parallelism, but then has answers provided to you at the end. So the best visual way I've sorted out over my years in this space to try and represent the true power of quantum systems is something like the following. Quantum systems, because they can temporarily be in multiple configurations at once, the way that you would describe that mathematically isn't with a single bit string. You would actually need to use an entire matrix to describe these states. And these states go by the name density matrices. And if you're further along in your undergraduate career, you may have been exposed to these things. The premise is that the density matrix picture is the complete way of representing information, quantum and classical. And classical is a subset of this full state space, as it were. So when you and I are performing operations on information in a classical way, where just it's bits flipping, as it were, you would be in that diagrammatic picture looking at something like this, right? So you have this full matrix here. I've turned it 45 degrees so it looks nice, where different individual elements along this diagonal are given these bit string numbers, right? So you go from all the way from 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1. And when you're performing classical operations, you're actually just sampling different individual bit strings, right? You're flipping a bit, which moves this one single black pixel back and forth on this line. And that is the total amount of information that can be possessed and processed according to classical information. It's one pixel in that giant space. What you can get with quantum mechanics is a much richer occupation of this full square here. And not only just in terms of black and white, but you can have all colors, where the color can be used to represent phase information. So all of that information is available to us if we were just able to harness quantum mechanics productively. And so I will just use this opportunity to describe an intermediate quantum technology, a quantum computer made by some good friends of mine down the hill at D-Wave, where they are making use of quantum mechanics to perform calculations, but not the entire quantum space. So they are able to access part of this quantum space, and they have a method wherein their algorithms are sampling part of that space to help them arrive at an answer, where you open the Schrodinger's cat box and it tells you an answer at the end. And with some probability, it's more efficient to use those tools than to do a classical approach. There's a lot of discussion around that, but it's very much a partial quantum computer. It computes things using quantum mechanics, but does not have universal access to everything quantum mechanically. Whereas what we're trying to do is access this full space. And this diagram may look a little bit over the top, but the point is that these kinds of states, this information capacity is available to quantum systems. It is the sort of thing that we're trying to build. And even if that isn't the specific state we would want to build, the principle is that we could. We're trying to build something universal. And what you could imagine is by having access to this universal large-scale system, you can get at solutions much more efficiently if you can make use of that large space, but then have succinct answers at the end. So the kinds of problems that everybody in the field is very excited to try and attack using these systems are the kinds of problems where you need temporary access to extremely large state spaces, but then the answers can be quite succinct at the end. And so needle in a haystack kinds of problems, finding minimum energy configurations, things for logistics, chemical simulations, and even, yes, code breaking fit into the kind of categories of algorithms that you could have using, or you could access exponentially more quickly using a quantum processor than you could with any classical means. And so what do I mean by exponentially faster? I don't mean every single time it's going to be faster. So I think the important point to drive home here is it's a scaling question rather than a sheer speed question. So this is one of the early works where we took a look at a particular quantum algorithm. Now there's dozens now. If you want to go look them up, go Google quantum algorithm zoo. It has dozens of algorithms that have been worked through. But this is one of the early famous ones where they did some resource estimates as to what you would need for a quantum computer to do something that couldn't be done using classical means. So the idea is that you could try and factor a large number. And this is a computationally challenging thing. If you have a large number, which is the product of two primes, it's very difficult to actually figure out what those two constituent primes are. And so the best known approach to do this scales quite badly with the size of the string, of the bit string. So what this means is that, for 100 bits, it can be done rather quickly, but the problem grows exponentially. And if you're even just working with 1,000 bits, the chances are that you're going to probably not live to see the result if you're trying to solve it using these classical information processing approaches. But if you're able to use this exponentially large state space, you could achieve these things, which on the small scale would actually be slower, right? So these are these quantum algorithm curves for different clock cycles for that computer, for that classical computer. And for, a slow quantum computer, you'd still probably not find it very valuable. But for a fast one, you can imagine a scheme in where you could actually meaningfully address these kinds of questions on a reasonable time frame. Now, a lot of these kinds of estimates have been revised and changed, and there's many, many caveats to all of these, but it gives you the point is that it's not that it's always just faster. It's not just a sheer brute force. It's that by using different techniques to solve the problem, you have the hope of attacking these computational challenges through means that just can't be solved any other way. It would take the lifetime of the universe to use it using classical techniques, but quantum techniques have a go. And so when I want to drive home, it's not just the exponential speed up side to it. Quantum technologies as quantum information has different rules, right? We can play by different rules and try to make technologies that couldn't exist any other way. And so the exponential scaling is one of them, but there's a few others that quantum information can offer that can't be done any other way. And one of the that don't need lots of qubits or lots of time. So something as enticing as the term teleportation, you can actually teleport quantum information from one place to another. I believe the record distance is a few hundred kilometers now. So it's really truly remarkable that relies upon the fact that quantum information is just different in the way that it is encoded and held compared to classical information. And one of the consequences of those kinds of laws, it allows you to do these so-called quantum networks. So there's a whole category of technologies that could be unleashed if we were able to sort out a few engineering challenges, sincere, but engineering challenges around distributing entanglement. So quantum entanglement is the resource that was used. And if you haven't been introduced to it yet, you will be. Entanglement is the resource used to allow teleportation, but it's also a resource that's used for this kind of exponential speed up. Those large, complicated density matrices are almost all entangled matrices. Okay, so this diagram here is showing you that you can use pairs, little nodes, quantum nodes, to entangle things that had never actually directly interacted. And so in doing so, you can actually generate long distance entanglement that could then be used for, say, global teleportation. We've done teleportation at small scales, but this kind of building to larger entangled networks is a dream of many, and we've been working towards it for a good number of years. So what I'll raise here is that actually these are very deeply connected topics. It's not just computation and networking and even sensing. This is very much a integrated technology where there are many different physical platforms that are trying to do many parts of it. But where I see it in terms of the race and the way that the race is moving is this movement towards this integrated quantum computing network. Now, of course, this is kind of the longer term ambition of the space. People are interested in these so-called individual short link teleportation challenges. And then there's different stages of complexity one can add. And so this is, thinking about networking and making quantum networks more exciting. Quantum networks also offer unhackable cryptography, which is just a really nice change from the kind of cryptography and the kind of communication channels we use with classical techniques, where eavesdropping and certain other negative consequences are all too common. With quantum technologies, you have this kind of built-in security to it, which is one of the reasons why people are trying to build these larger technologies. But even seeing it from the computing side, quantum processors are going to be so much more powerful once they're integrated and networked together. It's the same reason why you get this exponential scaling. Every qubit takes that density matrix and multiplies it by 4, right, in terms of sheer size. It's enormous, and the scaling that you get is inherently different from Moore's law, right? Adding a single qubit really boosts the capacity of every system, and so the networking of quantum computers is going to be very central to the way that we process information going forward. And you as undergrads, you will see this in your lifetime. This will be a defining transition, in almost, in my mind, to the same level of transition that we've had from the last time we commercialized a branch of physics, right? And so I would point to perhaps the semiconductor industry, and we are still living with some of the longer term consequences of commercializing that branch of physics, right? It's just going to be tremendous when we actually do the same thing for quantum mechanics, and you will see it in your lifetimes. We are already starting to see little pieces of it. So you may have heard about this term quantum supremacy. So this was the first demonstrated event where there is a controlled quantum system on the scale of a couple dozen quantum bits or qubits that were able to together perform an algorithm that produced a result that would have taken apparently 10,000 years to do with a classical system using the best supercomputers. Now, remember about what I said about scaling. The actual ratio of those times isn't really what matters. It's the scaling. So it's that if you were to try and do this with, say, 54 qubits rather than 53, it would take, you know, twice as long, or whatever the scaling is for a classical system, whereas quantum systems could do it still efficiently. So there's a bit of noise, certainly a bit of a hype around this space. The algorithm that they did, this was Google's result. It was actually, it was just phenomenal result. And it was the culmination of a lot of work around a superconducting based qubit system. And it was completely useless as well. So the algorithm itself has no commercial value. It was very much a planting a flag in the sand moment where we, for the first time as a species, as it were able to use quantum mechanics, harness quantum mechanics for something that couldn't be done using classical means, classical computing means. So that was in 2019. In 2020, there was another so-called supremacy argument. Again, an algorithm that has very limited commercial value, if basically zero commercial value, but yet still was the milestone of outperforming the best known or any known classical approach to the problem. So I'll just say that this is a very daunting physical apparatus, and I feel bad for the team who had to actually carefully, painstakingly align all of this. But yet they were able to do something that couldn't be done using any classical system. And I'll note this particular advance also wasn't universal. So going back to D-Wave's case, there are non-universal things that could still show some so-called advantage. And the term quantum supremacy versus quantum advantage, there's a lot of mixed up language in this space around this. So I just encourage you to read carefully what they mean when they say it, because the terms, of course, it's a fast moving space and these terms are changing their definition pretty quickly. But nevertheless, it does mark a watershed moment in the space. People are no longer saying, oh, well, it probably can't be done, right? It's basically seen as inevitable now. It's just a question of when, and different people have different estimates, and we might all be wrong. It'll be interesting to see how it plays out, but it is very much the consensus in this space that it is inevitable. We just have to get there. So getting there is an interesting trajectory, and Canada actually is one of the oldest, or rather the first movers in this space. It's not just D-Wave, it's also the foresight of some early institutes, Institute for Quantum Computing. There was early work in Calgary as well, decades ago, right? Around 2001, and where people could tell that this was coming and they wasn't quite sure how quickly they could move. But I will just say that this is a bit outdated, this particular slide. However, it does show that that Canada is the home to a lot of really good industrial research as well as academic research. So as a space, it's been for the past 2 years very much an academic pursuit. And now we're starting to see this tipping point where we're moving from most of the research happening within academia to about, I would say, a third of the, in terms of R&D, is now happening within an industrial setting globally. And so this is being driven not just by the big names, right? So we'll have heard the Chinese result, and you heard the Google result. IBM is also a big player here, but there's actually quite a thriving startup space here because, of course, it's not really clear what the winning technology will look like. It's not the case that the fact that we have a superconducting system or a photonic system, that they hit these kinds of supremacy or these advantage claims that necessarily makes them the front runners. There's a lot of, there are many different platforms that people are actively pursuing and funding. And a lot of them have kind of different flavors to one another. So it's going to be very interesting to watch this space. If you take a look at other technologies that we've commercialized out of physics more broadly, there tends to be a trend where it starts off very promising, it stays in academia, and then there's this mass proliferation of startups and technologies and ideas, and everything's very exciting until there's a consolidation event around a dominant technology. And we don't know what that's going to be yet. But that's the space that we're in right now. It's the shift to industry and this really rapid progress, rapid progress. It's wonderful. But yes, Canada is definitely punching way above its weight, and things are it's partly attuned to the fact that we have really good training in quantum technologies across Canada relative to our size. So where is this going? Now, I've said that there are these kinds of applications where we were able to show something that couldn't be done using a classical processor. And that's true. And I also told you that there's dozens and dozens of algorithms that people have worked through that demonstrate exponential speedups compared to what can be done classically. Even something as important as chemical simulations. You don't have an efficient way of simulating quantum chemistry because they have the full complexity of quantum systems in them. So you really do need quantum systems to be able to efficiently simulate other quantum systems. So there's a big opportunity to use these tools. But there is a big gap between where we are and where many people believe we need to be to get something that has commercial value. And that's really where we're going to see this consolidation thing happening, is when we start to get algorithms that are forming and technologies that are forming the key part of some company's bottom line, right? That's when things are really going to shift. And so right now, so this is a figure from Google from a few years ago, where they projected forward their technology path, as it were, where they create more and more quantum bits. Because you'll note that the demonstrations we've seen so far, that only was 50 qubits, 60 qubits, right? Like, it's taken a number of years to go from 5 to 6 to 7 to 30 to however many qubits. And even 50 qubits is enough to outperform the world's best supercomputers, right? The number I like to throw around when we think about how scale works is that if you were to have a 300 qubit system, it would take more bits than there are atoms in the universe to write out the full density matrix, the full state, right? It's too big. But yet these systems exist in nature, right? So they have this complexity. And the challenge is, okay, well, what can you find that's valuable there? Because a lot of the algorithms that have been developed don't use 50, 60, 70 qubits. They're using, 1 million qubits. And that was the kind of pen and paper solution that people were able to arrive at when they're designing these algorithms. They're using limiting cases in many instances to say, okay, well, this would be commercially valuable, but you need 1 million qubits to do so. And so there was a big question, and there remains a big question about what is needed in the near term to get something commercially valuable to people so that we can adopt this technology and bring it mainstream, as it were. And it's still an open question. We don't know what actually exists in these kind of low qubit number regimes. The other thing I'll mention here is the error rate. So a lot of these qubits are noisy. Their control is basically analog, and they have all kinds of possible errors that they can affect them. And so the reason why you often need this many qubits is to be able to perform quantum error correction. There are a bunch of error correction algorithms that have been identified, and a lot of them seem to need a great deal, a large number of imperfect qubits to get a smaller number of perfect qubits. So this big gap is something that people are actively working on, and we'll see how that moves forward in the near term. But in the few minutes I have remaining, I'll maybe just explain to you a little bit about where SFU fits into all of this and why we've gotten a bit of attention for our technology. As I mentioned, there's a few different technologies that people are working at. And so some of them are kind of in earlier stages of development than others. Some of them are older technologies. Some of them are quite new. This is from an archive paper that I'm using just so that I'm not the one actually populating this table, is so I can cite it and not just give you my own personal argument for and against for each of these technologies. I do disagree with some of these for what it's worth, but I wanted to show to you the variety of what exists, and also speak to what our working principles here are at SFU, or at least within my lab here at SFU. We have a few quantum labs here, but within ours, we're working under the premise that basically, if you need to have 1 million qubits, you can't really compete with silicon. Like, the answer to a lot of the integration challenges over the past couple of decades, and honestly, the reason we all are so comfortable with the supercomputers in our pockets, is because of silicon. We're just able to make silicon cleaner and better and higher uniformity than any other solid state information processing task. So we are working under the premise that these things will be based on silicon, and they will be networked over telecom connections, right? This will be a network of quantum computers when we're looking back, right, in 30, 40 years, and I'm about to retire and can say, this is the technology that we've put together. So it's not just that it's silicon and telecom, it's that they also have to have good quantum ingredients. And the best, longest lived, some of the longest lived quantum ingredients are so-called spins, electron spins or nuclear spins in various configurations. So we aren't using any one of these. We're actually using a combination. Our technology here is using a combination of two technologies. We're using solid state spins in silicon, namely, and we're connecting them with telecom. And in doing so, we're actually getting rid of their argument against both of them. And we are truly getting the best of both worlds with the technology that we're putting together. And this doesn't always happen when you hybridize technologies. Often when you hybridize technologies, you get the worst of both worlds. So we've been very fortunate to be able to find something that does seem to tick all those boxes. And what do I mean by integrated photonics? So, so how do you combine optics and silicon? When you have a full optics bench, every single one of these, especially every passive component, doesn't need to be in this form factor. You can have an integrated version of every single element on this bench in an integrated format. And it's because in silicon, you have a high index of refraction material. That means you can bring everything down to a very, very small size. And you can actually print fiber optics and beam splitters and mirrors and whatever it is you need to print right into the silicon. And the technology that enables this is so-called SOI. So we have wafers of silicon. So the back is a silicon wafer. These are industry standard wafers, and we're using them in our labs here, but everybody else is too around the integrated photonics space. So we have an SOI wafer, a silicon on insulator wafer, where you have a buried oxide, which is a lower index material, and then this higher index material, silicon at the top, in the device layer, and then in the bottom handle layer. And if you print, if you etch down in a particular pattern, you will form these little channels where light can propagate. And remember, silicon is transparent to telecom wavelengths. So it actually acts as a guided light pipe, and you can wire it around and branch it off and do all of these things. This is integrated photonics. So you're probably familiar with integrated electronics on silicon, but you might not know that integrated silicon photonics is also the platform of choice for industrializing optics and linear optics. So just as a picture, you can have input-output ports, you can couple fibers in and out of this SOI, you can have these different structures that have these different scattering parameters, and all of this stuff can be very well simulated and is very well understood, and we're borrowing it from that engineering side of things. So again, for silicon, it not only has these commercial advantages, but it has phenomenal quantum advantages. And so I'm just going to point out a few things, both quantum for the spin side and quantum for the photon side. So silicon has a bunch of isotopes. It has 3 natural stable isotopes. And as a material, we can get it to be the cleanest solid material that we know how to create as humans. And so it was actually used silicon was used to redefine the kilogram in the so-called Avogadro project. And what was done for that project was it required the purification of these isotopes so that there was one single isotope, and the number of silicon-28 atoms is used now to redefine the kilogram, which is just amazing. But in doing so, what you do is you remove these so-called silicon-29 nuclear spins. And by being an odd number, these nuclear spins have a spin to them, non-zero spin. And that acts as a very, very faint source of magnetic noise. So when you remove that, you actually get phenomenal coherence times. And I'm not going to go into this other than to say SFU in doing so, Canada has actually been punching way above its weight in terms of the longest coherence times, the longest lifetimes that a quantum bit can have before it decays. So the Schrodinger's cat analogy is how long can the cat remain dead and alive before it collapses on its own to one of those 2 states. So Canada has actually been way above the rest of the world on this front for a long time by virtue of its access to this really pure silicon. Now, by working with this ultra pure kind of silicon, you actually get much better optical properties as well. So this is one of the early results where we took a look at what was known as it's an optical luminescence line for a particular spin defect in silicon, where you go from having this broad line to having spin resolve transitions. So you can already start to see that there's a lot of potential for using spins and photons all in one integrated silicon platform. So the sad thing about this particular center, which is why, given its early result, didn't spur the work that we're doing now here at SFU, is because people did not believe that they had very good photon properties beyond the fact that they were well defined. They didn't generate very much light. So this was the reputation of silicon prior to our arrival on the scene, that basically silicon was great for the spins, great for electronics, great for photonics, but it just could not generate the light. And what we found actually in the past couple of years is that's exactly wrong. There are lots of centers that generate lots of light, and we just had to go looking for them. So they're called silicon color centers. There's a broad category of silicon color centers. We're the first lab to really focus on this so-called spin photon interface in silicon. There's a number of them. They are formed by basically forming just little breaks in the regular lattice and replacing, maybe there's vacancies, maybe there's replacement other atoms. They tend to have very reproducible structures, and you can learn a lot about them through spectroscopy. And fortunately, by virtue of working in silicon, you can usually look up a lot of their properties because they've been studied for decades. So what we have seen is a few different centers that do generate quite a bit of light, and they do generate light in the telecoms bands. So these are 3 examples. We have a paper out on this from 2018 that talks about these specific ones. They're good at generating light, but sadly, these specific 3 do not seem to have good spins. Fortunately, the ones that I'm about to show you next do. So this is the workhorse for a lot of our technologies now. It's called the T-center. It generates light in the telecom band, and it has a whole bunch of spins that you can use to hold on to quantum information. And so there's a lot of properties that you can look up. But what I'll kind of skip through rather quickly here, just to kind of give you the punchline. So one of the things that you might ask, well, why 1326? For those of you who are familiar with telecom frequencies, why not 1550? There's actually a few different centers that we are looking at, and we like this one the most because it's very close to the so-called zero dispersion point for the dominant global telecom fibers. So it will allow us for longer distance networking more easily. So what was known prior to our work was basically this center, its structure and its wavelength. And we've since gone through and found out a whole bunch of properties that may basically all give you the green light. It's go, 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 go. Things are going to work pretty well with this quantum technology. And I'm happy to answer questions about any one of these specific technical metrics. But what I do want to kind of flash up in the last concluding minutes of my talk is the fact that we can, when we make individual qubits in silicon, we're not talking about making 1 or 2 or 6. You make many all at the same time. You're using the industrialization of silicon to get to go from 0 to 100,000 pretty quick. So what we were doing in these experiments here is we made little so-called micropucks, where we have qubits inside these T-center qubits in each of these little pucks. And this was the SOI layer. This is the device layer of that SOI structure. And by presenting them as little pucks this way, what you're doing is basically forcing the light out. So one of the things about silicon, what keeps the light in, which makes it great for an integrated photonics platform, makes it very hard to go and use a microscope and see these individual spin photon centers. So if you were to compare like a slab mode within the SOI, where this is just a layer of silicon, most of the light actually stays within the device layer. It acts as a guided mode. But when you talk about these pucks, they actually boost the emission outwards. And so you can see them with a camera. And that's exactly what we did. So we have a cryogenic camera that was going and taking a look at each of these pucks and taking a look at the luminescence signal from these individual single qubits. And this chip in particular, I think this one had 30,000. So it's really a different approach, right? When we're talking about, when you're thinking about the linear optics approach, where it's like like the Chinese demonstration where it's actually a table. Or you're talking about the superconducting systems where, you know, adding a single qubit is like a lot of other wiring infrastructure and dilution refrigerator work. Here we print them, and really there's no difference between printing 4 and 40,000. So we're going to go with that scale first, and then thinking about, you know, these aren't entangled. You don't want to compare these things as apples to apples, but it is really just emphasizing that we're not going to worry about qubit number for this kind of technology. At this stage, we're going to be now thinking very much about how to use the telecom photons that are emitted from these things to generate the networks, generate the computers, and generate this larger technology that have been kind of lighting so many fires for so long now. So with that, I'm going to conclude. This was a picture that's not lining up with the names here, because this was one of the last pictures we could get before COVID made this a security risk or a health risk. But I did want to specifically highlight in this work the foundational work of Mike Thewalt, who is a close collaborator of mine here at SFU, and what I describe as Mr. Silicon, who just understands silicon spectroscopy and has been looking at that for a number of decades. The quantum technology aspect is the broader motivation of most of the people here. Some have left, but a lot were growing. And I would just emphasize, we are hiring across the board. Please do come if you're a rock star and want to get involved in this kind of work. Let me know. There's a lot of work to do, but it's very exciting. We work on SFU campus, which is on Burnaby Mountain, which is in Metro Vancouver. Sometimes you get these inversions, which is just wonderful. You can go walk out on the promenade and go take a look, and you're kind of over an ocean of cloud. The actual ocean is right down there, and then off to the left there. Our lab is right here, and so once it's allowed, please do come visit. Drop me a line. Love to show you around. And I'll just do one last little plug. I was mentioned we have a company that's spinning out this stuff too. So if you're interested more on the corporate side, I'm all ears. Come and talk to me. So with that, I'm going to thank you very much for your attention, and I will turn it to questions.
Thank you, Dr. Simmons, for a very interesting talk. I'd like to hand over to Dr. Heilman now for the question and answer. Thank you.
Sure. Yeah, as Saria said earlier, please, if you have any questions, submit them to the web form that is linked in the description of the YouTube. We have a couple in the chamber here, Steph. So the first one from relatively earlier in your talk, how can you force a particle's state to be something that isn't an eigenstate? Specifically, if the states are spin, how can you force a particle into a superposition of spin states?
Oh, that's a wonderful question. So fortunately, we don't have to invent that either. So the technology behind MRI does this for you. So MRI uses magnetic fields and coils, and by driving time varying coils that line up with the frequency of the transition, you can actually drive transitions. And so this is really the basis for most quantum control. You'll have the same, very similar physics for superconducting systems, and photon systems are a bit different. You'd use like physical systems like beam splitters and that kind of thing. But usually, yeah, that's how it's done. We don't need to define any of that. We can borrow decades of research. It just wasn't called quantum control. It was called NMR or similar.
Great. All right. Next question, a little bit more on the sort of the larger picture side. Is there a specific company or institute you personally believe will win the race to make a quantum computer, and why? And maybe you should leave yourself out of this. I don't know.
Well, okay, yeah, I should leave myself out of that. I'm very bullish about our technology. If it's not us, it's going to be something like us. So it's going to, in my view, I just think the long-term winner is going to be silicon, it's going to be telecom, and it's going to have some memory capability. Now, on the way there will be many winners. I think on the way there will be lots of different technologies that can show these kinds of quantum advantage things, and that's great. I mean, it's only good for the field. I would also say that there are other quantum technologies that don't necessarily need the full infrastructure of a full quantum computing network. So quantum sensors are a very useful technology that don't necessarily need the full infrastructure that I'm talking about here, and that will be a winner in its own right as well.
Great. So we have a couple questions that I'm going to kind of group together into one about engineering challenges. So can you elaborate and tell us a little bit more about engineering challenges for quantum tech, and maybe what the next big hurdle that you imagine needs to be overcome is?
Wow, that's a great question, and I can talk about it for a day, because every single system at the moment, the most promising technologies, have their own challenges, right? So you can kind of go into each and every single one of them and talk about what those engineering challenges are. But I don't see many of the challenges being faced by the most prominent technologies as insurmountable. They just might be too expensive to do, or they might just require a level of perfection that people aren't willing to build up, or it'll take a long time. So I can go through each of the individuals. Some technologies, they're solid state technologies, but aren't using silicon. So one of their engineering challenges is, okay, well, can you do all the fabrication that you could do with silicon, for example? Like that would be one engineering challenge. For the superconducting systems, temperature will just be forever a thing that they have to deal with. At the moment, they have lots of wires going down, and for everything except for a very small number of systems, it's almost a wire per qubit. And that just is not going to be something that scales to millions of qubits very naturally. So the multiplexing of that. The other one around superconductors is the footprint. And, you know, there are lots of different companies talk about their own roadmaps and how they would overcome their own individual challenges. Ion traps have something different. I mean, there's a lot of different things, but one thing I would say is across the board, a lot of the challenges are going to be the rest of the stack, right? So I'm talking just about the hardware so far, but there's a lot of challenges and a lot of developments that could go into some of the rest of the stack. For example, when I was talking about how you need like 1 million qubits to be able to do something error corrected with quantum systems, if somebody could take that from being an overhead of 1 million to 100,000 by just having better theoretical work on that space, that would help everybody. Another one would be a quantum algorithm that didn't need more than a couple dozen qubits, for example, and that would work well in a noisy environment before we have error correction. These kinds of things would absolutely, they're an engineering challenge, but they're more of like a software engineering challenge, but they're just as equally important to getting this thing to really take off.
Great. So we still got a few minutes. If anybody else wants to submit a question, go ahead. I guess I'll follow up with one just to give people a little bit of time. Kind of following up from what you were talking about, the superconducting systems and having like a scalability issue with temperature. Are any of the, to your knowledge, materials that are being examined for high TC superconductors appropriate for this kind of work that would help to manage that sort of overhead?
Well, that's wonderful. Yeah, so I think actually that was one of the original motivations behind D-Wave having the name D-Wave. I think that they originally imagined that they would use D-Wave superconductors to use at higher temperatures. I think the challenge behind that is the thing that is limiting the superconducting qubits in terms of their performance has to do with the so-called T1 time, or the relaxation time. And although you could use other materials to produce these qubits, and people have, it's the manufacturability is more challenging for many of them, but also the quantum performance is lower, even at the same temperature. So that is my understanding of that. I don't know if that's changed over the past couple months. If I haven't noticed a breakthrough paper in the literature, but that's my current understanding.
Great. Someone would like to know if any governments have shown interest in quantum computing, I guess maybe directly through your lab or contacts you have in industry.
Yeah, that's a great question. So government has played a role in this since day one almost. So they played a big role in IQC, and they've been playing a role in the US side of things through the NSA and other mechanisms for a long time, DOE, DARPA, those kinds of programs. Yeah, the EU has its billion-euro flagship program. The UK has £500 million on quantum technologies. Everybody is seeing this as a critical resource going forward, and rightly so. Like when you think about the ability of quantum information, quantum computers to at some point in the not so distant future be able to basically take apart all of the encryption on the modern internet, it really does scare people. And so the idea of actually setting up those quantum networks that are provably secure and getting those up and running, I mean, it is a big national security question, but it's also a big opportunity, right? Like we've seen this song before, we've seen this story before, where you have this major technology that ends up underpinning a lot. You can see what this trajectory is going to look like. We don't necessarily know the exact timing of all of these steps, but those steps will occur. And so a lot of many forward facing or future-focused governments have been thinking about this. The Netherlands has been putting on a bunch, and of course Canada has been in it from day one. Admittedly through its distributed programs such as like CFI or NSERC or the rest of it, but they definitely recognize it as a core technology that we could win at competitively globally because of our early investment in this space.
Great. We've got one more that has come in here. Do you think that quantum computing will help us solve some of our pressing societal challenges in the future? For example, climate change, pandemics, things like this. Will there be applications in those spaces?
Yeah, so I'm going to give the prepackaged answer to that. But I will just say we don't actually have these technologies yet, and it's kind of remarkable that we already know of categories of things that it will do before we even have them up and running. The one that's typically the kind of case in point that people point to when they talk about climate change for quantum processing is about improving logistics and agriculture. So logistics right now is a huge driver of greenhouse gas, just from ability in moving stuff around is a giant challenge. And if we could do that more efficiently and move stuff around less or move people around less and accomplish the same goals, it would have not just cost savings, but it would also be better for the environment. The agriculture one is about understanding the way that nature does things more efficiently than we can do synthetically. So there's this so-called nitrogen fixation problem that people mention frequently as a kind of nearer term goal, but there are a whole host of goals that you could try and hit if you had the ability to simulate quantum systems much better than we can. So the other one is, of course, drug discovery, right? Like we can't really well simulate the interaction of molecules. We can approximate and have all these, good methods for trying to approximate it, but those approximations break down. We have no ability to, for example, simulate insulin properly. It's just beyond the scope of classical systems and will forever be beyond the scope of classical systems. So if you had the ability to simulate these things properly, just imagine what that would have in terms of knock-on benefits to R&D around insulin or drug discovery or around this nitrogen fixation challenge where you can try and produce fertilizers as efficiently as nature does, rather than this 100 times less efficient process that we're currently using in industry.
Great. I guess, Saria, you can kind of cut me off whenever you think we're getting to time here, but another question's come in. What properties makes the quantum computing applications to cryptography unbreakable?
Can you say the question again?
Yeah, it says, what properties make quantum computing cryptography unbreakable?
Right, okay. So one of the nice things about quantum systems, well, nice and this is a double-edged sword. There's a property of quantum systems called the no cloning theorem. And the no cloning theorem is it simply states you can't copy quantum information. You just can't do it. You can try and approximate it, but you'll never actually copy that quantum information. And so you can set up, and the other side to it is of course this kind of Schrodinger cat picture, where if you measure a system, if you extract information about a system, you necessarily perturb it. So the combination of those two things allows for a kind of protection in terms of the way communication works. So for one, you could just teleport information, and that's secure in that it doesn't actually travel through intervening space. It actually is one quantum system distributed across two things that you can then hop in your quantum information and teleport it over. It's wonderful. So that's one way you can be secure. But the other way is connecting to this eavesdropper point and this disturbing you must disturb, or you must perturb quantum states premise. So in that picture, if you're trying to distribute quantum information, you could set it up in such a way that any observation of that quantum transmission can be detected. And the second one is you can't, the eavesdropper can't just copy the information and save it for later, because even the act of copying it would be detectable. So you have this kind of built-in security, which is lovely. Now, it doesn't keep them from stealing it, right? So somebody could come and steal the quantum information, but you couldn't copy it. So you could detect if the channel was broken, but you couldn't. They couldn't just hover and observe the transmission. So there's a lot more to it to that. It's very, I'm just kind of talking really broad strokes, but that's kind of the guiding principles which underpin that.
Great. I think that's all the questions we have in the chamber for now. So I'll pass it back to Saria, and you can walk us out.
Yep. Thank you, Jesse. And before I thank the speaker, Dr. Simmons, once again for the wonderful talk, I'd just like to remind the audience that the next CAP lecture is next Tuesday. So please come and join us next Tuesday for the next lecture. And to conclude, thank you, Dr. Simmons, very much for your talk. It was wonderful. So thank you very much. So
It's a pleasure to be here. Thank you.
Have a good evening, everyone. Bye-bye.